All right. So we can look at this other type of electrophoresis, which is 2D geoelectrophoresis. And before we start looking at 2D geoelectrophoresis, in the previous type of electrophoresis that we are talking about, which is isoelectric focusing, I forgot to mention something very important: the resolution of isoelectric focusing. Isoelectric focusing has a very high resolution. Why? Because I mentioned something like there are 20 types of different amino acids, and each one of them has a different isoelectric point. So which means this isoelectric focusing electrophoresis can even separate proteins with the narrowest uh, isoelectric points, as narrow as even 0.02 pH units. So it has a high resolution, it is efficient, but the problem is, everything that is efficient, everything that is nice has a problem. The problem is that it it is only limited to proteins. So we can now look at the 2D geoelectrophoresis, and I am happy to mention that because we've done the two types of electrophoresis. In fact, we've done SDS page, we've looked at an isoelectric point, then we are set to look at 2D geoelectrophoresis. Why do I say so? It is because this type of electrophoresis is simply a modification of SDS page geoelectrophoresis. So the difference is that it uses two perimeters. It uses two perimeters. That's why it is called 2D, two-dimensional. That's 2D electrophoresis. So the separations in this is done in two rounds. The first round, or the first perimeter, is based on isoelectric focusing. So the first separation is based on isoelectric focusing, and the second separation is based on molecular weight. So this type of electrophoresis is very, 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 very efficient. Why? Because we have situations in which we find protein molecules which have the same molecular weight. And these other types of electrophoresis tend to fail to deal with such type of molecules which have the same molecular weight. They are limited to separate such type of proteins. But this 2D geoelectrophoresis takes advantage of the fact that it applies two rounds. The first one is based on isoelectric focusing, or isoelectric point. Then the next one is based on molecular weight. So what happens is that the first round, just as I said it, if you remember how we are doing the isoelectric focusing, but let us not do that. I would like us to put this first round on a paper plate, on just a plate. So we know that when organic ampholites are used to make the separation medium, you have a gradient, portions of different pH values. So what happens is that when you apply proteins to this, and let us do this. So here we'll have negatively charged cathode and a positively charged anode. So what happens is that when proteins are put in here, a protein mixture, a protein sample which has a mixture of proteins with different charges is applied to this plate, and an electric field is applied to this field, what will happen is that different proteins will settle at different locations where they are at their isoelectric points. So they will settle. That's the first round. And after this, you will find that even though they have maybe the same molecular weight, we're looking at if this is the situation. We want to see the efficiency of this. So the efficiency is that if the molecular weight is the same, what happens is that the isoelectric point will do the first job, regardless of the difference in the molecular weight. Proteins of different isoelectric points will settle at their different regions where they are at their isoelectric points. So after this same plate is taken just the way it is, since the proteins have already separated using the isoelectric points, though they have the same molecular weight, they've already separated. Then now we can put them in another chamber. So let's say this is the 3-1, this is the 6, this is the 9, depending on their isoelectric point. So we get the same plate and apply it to a certain chamber. And when an electric field is applied there, when an electric field is applied to this chamber, migrations will start. So what you will notice is that since the proteins have the same molecular weight, then they will travel the same distance. This is the modern SDS. So after using the isoelectric focusing, we apply it to an SDS page type of separation, and we'll notice that the bands will form at the same distance. Why? Because SDS page mostly depends on the molecular weight. So since they have the same molecular weight, they will travel the same distance and they'll settle there. But the goodness is that we had already separated them using their isoelectric point. So there will be at different portions, but the distance traveled will be the same. So that's all about 2D Geoelectrophoresis. That's basically what we can talk about, and it is more efficient than any other one-dimensional electrophoresis, because it can even separate protein molecules with the same molecular weight, and that gives its advantageous and propitious what